Another type of solid is a network covalent atomic solid. So we're going to look at carbon. Carbon exists in several different forms. When you have different forms of an element, they're called allotropes. So carbon can take the form of graphite. Here's naturally occurring graphite. And if we zoom in and look at the structure, we see that graphite's composed of carbon atoms that are covalently bonded to each other, but in a two-dimensional way. So there's a layer here of graphite, and there's another layer and another layer. The layers themselves are covalently bonded, but between the layers, they're held together by intermolecular forces, which would be just dispersion forces. So those dispersion forces are weak, and that causes these layers to slide relative to each other. So graphite is slippery. That's why it works well in your pencil lead, because as you push it across the paper, layers slide off and leave a mark behind. It's also used as a lubricant. It's a good electrical conductor because it has extended pi bonding across this. So molecular orbital theory, we have pi bonding extending across, and so the electrons can move through that pi network and conduct electricity. Graphite has a density of 2.2 grams per cubic centimeter. You don't need to remember that, but if you look at a diamond has a higher density, a density of 3.5 grams per cubic centimeter. Graphite under extreme pressure can rearrange and form diamonds. In a diamond, we have hexagonal structures here, but now the covalent bonds extend in all three directions, all three dimensions. And so it's covalently bonded in all three dimensions, and therefore it's very strong. It's not going to be slippery like graphite is because the layers don't slide. So diamonds form naturally underground. They can also be synthesized. It takes pressures of about 50,000 atmospheres and very high temperatures like 1,600 degrees Celsius. So changing carbon in the form of graphite into a diamond is not a simple matter, but it can be done. If we look at the structure of the diamond, its unit cell is similar to the zinc blende unit cell. Here's the zinc blende. So that was a face-centered cubic, and we had these zinc ions in 4 of the tetrahedral holes. Here we have carbon atoms as the lattice points in the unit cell, and 4 additional carbon atoms occupying tetrahedral holes. You may remember carbon likes to form 4 bonds, and so it'll tend to do an sp3 hybridization and get a tetrahedral shape. Diamond has a very high melting point, 3,800 degrees Celsius. It's very hard. It conducts heat well, doesn't conduct electricity. Because it conducts heat well, it's useful as an abrasive and as a cutting tool. Abrasives, when you polish something, there's a lot of friction. It can generate a lot of heat. Because diamond can transport that heat away, it's good as an abrasive. The reason it's very hard and has such a high melting point is it's held together entirely by covalent bonds, which are very, very strong. Back in the 1980s, a new form of carbon was discovered. They did this by aiming a very strong laser at a carbon surface, kind of just to see what would happen. And they made things like this. This is 60 carbon atoms in one large unit. It's not really a molecule, but it's 60 carbon atoms covalently bonded together. So this is called Buckminster Fullerene, and of course there's a history behind that name, but they're soccer ball-shaped clusters of 60 carbon atoms. Fullerenes in general, also known as buckyballs, contain clusters of from about 36 carbon atoms to more than 100 carbon atoms. So you can make one that's C60, but you can make other sizes as well. And researchers have been busy doing other things with graphite or carbon. So nanotubes. Nanotubes are a lot like a roll of chicken wire, if you're familiar with that. So this is a single-walled nanotube. So we have those 6-membered carbon rings that are interconnected. It's all covalent bonds. And this is in the form of a tube, and it could be very long. So you can have a single-walled tube. You can have a multi-walled tube where you've got lots of different tubes nested inside of each other. These nanotubes are really strong. They're 100 times stronger than steel, but only 1/16 as dense. And so they're very useful for things where you want something to be strong and yet lightweight. Things like golf clubs, bicycles. Anytime you see like a graphite golf club, they don't mean the slippery stuff in the pencil lead. They mean nanotubes, carbon fibers as well. You can make graphene ribbons and graphene sheets. So we talked about graphene at the beginning of this chapter, the Friday night experiments where they kind of discovered this by accident. And so this is a 1-atom thick sheet of carbon. You can take bundles of these nanotubes and form very small wires because graphene and these nanotubes do conduct electricity, and so they can be used as wires even though they aren't metals. Another type of network covalent atomic solid is a group of things called silicates. And these are extended arrays of silicon and oxygen. So silica has a formula unit of SO2, and that looks like a molecular formula, doesn't it? You got 2 nonmetals, and we think, oh, those are molecules held together by intermolecular forces. The difference here is that the silicon and the oxygen are covalently bonded in an extended array. So it's not discrete molecules. It is a covalent atomic solid. Silicates are very common. The most common network atomic solids, they make up about 90% of the Earth's crust. Sand is mostly silicates, silicon and oxygen. Quartz is one form of silica. There's a lot of different forms. So in this extended array, which is a little hard to look at because we've got a 2-dimensional screen and that's a 3-dimensional object, the silicon is in a tetrahedral hole between the oxygens. And then this oxygen would be bonded to another silicon atom. When you look at the Lewis structure for this, these oxygens have a lone electron here, right? You're like, that's not right. Well, it's okay because that's just one part of it. What we've got here is that there's another silicon over here that's bonded to oxygens. And so it just goes on and on like that. So there's not any discrete molecules. Any questions?